Hi, the IBM Advanced Data Science specialization on Coursera has been enlightening and utterly enriching. This is my final project with the course, Marketing Analytics, Modeling Customer Subscription Preference. I am Adejokun Adedamola Emmanuel from the blessed country of Nigeria. Let's begin. So, a little background before we delve in further. Targeted marketing campaigns are a very effective means of reaching prospective customers. Such campaigns, however, must be predicated on an empirical and systematic framework. A predictive classification model obtained from a supervised machine learning algorithm affords us such a framework. Sections of a prescribed customer base can be set aside for preferential marketing outreach based on the output from such a predictive classification model, thereby saving an organization scarce human and capital resources. The data set that has been generated from a telemarketing campaign to sell long-term bank deposit subscriptions of a retail bank is employed to train our predictive model. The data set is obtained from the UCI machine learning repository. The link is displayed. Conceptually, as is the case with all machine learning, okay, almost all machine learning pursuits, the data set is split into a feature set and a target label. The feature set in our own case comprises of the client related data, contact center related data, and associated socio-economic indicators. There are 41,188 entries along with 21 features, 20 of which comprise the feature set. Feature engineering involves optimization of the feature set such that it is amenable to classification machine learning algorithms. This is usually involves, but certainly not limited to, feature selection, feature transformation, dimension reduction, and feature creation. For our case study in particular, we're going to implement feature selection, running iteration with or run iteration of pre-processing and exploratory analysis alongside. So it's going to be like an integrated step sort of, because we can seldom run pre-processing and exposure analysis in isolation of feature engineering. So everything is just integrated. So that's what this section is going to do. Preliminary exposure analysis reveals an imbalance in the target label as indicated in the graph. If you see the yes class of the target label, which is the subscription status, is much less in magnitude than the no class. So our problem is essentially an imbalance classification problem. So going further, before we proceed with more exploration, the feature selection step is implemented. Background to the selection we're about to make is that the assumption in this study, the fundamental assumption, is that the client subscription preference is based upon an underlying propensity. In other words, a client usually has a preference before being contacted by a telemarketing campaign, and that is what we're trying to predict. Yeah, that underlying preference, propensity of a client. Yeah, that makes them make a choice. Yeah, have a preference. So that is what we're trying to predict. So yeah, so the objective of our modeling is to try and predict a client's preference before they are contacted. Yeah, so that we can save costs and improve turnaround time. So this essentially implies that the contact center related data and data that has to do with the agent that made the call, how long it took the agent to convince the prospective client, and all such data are relevant because it defeats the purpose of the predictive modeling, which seeks to predict such preferences before a call is put across. So we have a customer base, then we seek to predict the portion of the population of the customer base, that has a higher potential of subscribing. Then we target such group without having contacted them earlier. So all such contact center related data obtained from the original data set are redundant and wouldn't help us in our modeling. So they are all dropped. Eight in number. Going further. So the categorical features have widely distributed entries of unknown. So we make visualizations of the features, categorical features, to see the extent of the distribution. So for the job feature, if you look here, the unknown entries not so significant. Same for the education feature. For the marital status feature also, there's no unknown. For the loan feature, we have just a slight proportion of unknown as against the entire complement. Same also for the housing feature, but for the default feature, the unknowns, the unknown entries are quite large. Another thing to note here is that there is, at least based on the visualization, there is no yes class. There is no yes category. So the feature essentially doesn't have information content, since all the entries are under the no category. So it is redundant. So we are also going to drop the default feature subsequently based on this exploratory analysis. So so the foregoing chart reveals we have a lot of unknown entries among the feature sets, even though they are not evenly distributed among the features, but all such entries are subsequently dropped. In addition, like I said earlier, the default feature is also dropped for reasons already delineated. So next, the numeric features are explored using box plots. So these also give an indication of the information content of the features. For the age feature, the first feature over here, you see that there's a very good overlap between the box plots of the target label, the yes class, and the no class, relative to the age feature. So that means the information content is not so great. But for the employment rate, if you notice that the box plots aren't as much overlapped, so we have some protrusion from the no class of the target label, but the consumer price index is also closely overlapped. So that also has not very high information content. So similar reasoning can be applied to the remaining three features. We go on to so after the feature engineering and associated pre-processing and exploration analysis, our data set now contains 30,488 rows, 12 features, 11 of which comprise the feature set. The data set is now loaded as a Spark data frame in preparation for modeling. It had been previously loaded as a Pandas data frame, but now we're going into modeling, so we load it as a Spark data frame. So on to modeling. So we're going to be modeling on an Apache Spark engine. So Apache Spark is a fast parallel cluster computing engine that is widely adopted for scaling data science projects. The Spark ML machine learning model of Apache Spark is engaged in this project to train the predictive model using the PySpark API, which is Python's syntax interface with the Apache Spark computing engine. The customer preference prediction is a binary classification problem. Yeah, since the target label has either a yes or a no. So logistic regression, support vector machines, random forest, and graded boosted trees are all applicable. And we're going to use each of these algorithms to train a model and get the best performer out of these. So moving forward, yeah. So before the algorithms are implemented, Apache Spark has a unique architecture. So before we can do anything, modeling the categorical features, including the target label, are indexed. Index features are one hot encoded. Vector transformation of the feature set is effected. The feature set that had been vectorized in the previous step is normalized. Then we split the data set into training and test sets, 80% to 20%. Moving on. Yeah, so the significant, the essence of model evaluation. It ensures that the eventual output of our model is both consistent with our initial objectives and is in no way misleading. Yeah, so it's spot on, and we are able to make credible and sound decisions from such model. So that's what evaluation gives us. Yeah, to ensure that our model, the output of such model is spot on. So an iterative phase between the feature engineering, modeling, and evaluation steps is usually in place to ensure the best possible model performance is derived. Yeah, since our problem is an imbalanced classification problem, we employ the precision and recall evaluation metrics to ascertain the performance of our train models. These metrics are more suited for our use case, which is imbalanced, which has an imbalanced target label. Moving on. Yeah, so the output of preliminary modeling is given below. So we can see the metric results for logistic regression, support vector machine, random forest, and graded boosted trees. So the random forest and graded boosted trees have comparable performance. However, the random forest model is preferred for its lower computational costs and it being amenable to parallel computing. Yeah. So at the moment, graded boosted trees do not support parallel computing at the moment, but with the way technology is fast improving, I'm certain that will change soon. Yeah, so random forest, being the most promising algorithm, is subsequently subjected to hyperparameter tuning using the cross-validation and grid search feature of Spark ML library. So the final metrics obtained after we implement the hyperparameter optimization with the random forest algorithm is given, is shown. Yeah, so the F1 measure is 0.849. Yeah, which is not outstanding, but yeah, decent. So before we conclude, I'd like to just quickly run through the code. quickly run through the code just to give you a feel of the modeling aspect, especially. Okay, so this is the Spark session that is required to load the data set as a Spark data frame, and we have to explicitly define the schema so that we don't have problems downstream when we are indexing and doing all those other stuff. Then some column renaming, also to avoid some issues up front. Okay, then just go straight to the modeling part. Yes, so this is code for logistic regression. So you have the logistic regression constructor. This is our object. Then we have the pipelines, the indexer, like I said before, encoder, assembler, normalizer, and logistic regression object all comprise the pipeline. Then we use the multi-class classification evaluator for the evaluation, the record, the F1, and the precision metric are taken. Then we use this code over here to put it in a Spark data frame. So similar codes are run for the support vector machine and the random forest trees, as well as graded boosted trees. So these are all the preliminary modeling before we put all of the metrics in a table, and we see that the random forest and graded boosted trees are the top performers, but we go with the random forest trees because they have less computational cost and they are amenable to parallel computing. So this is the final modeling stage where we tune the random forest parameters. This is it, using the cross validator and param grid builder of the Spark ML module, and voila, we get our final metric F1 measure of 0.849. So to conclude, so a model has been trained to predict customer preference for purchasing subscriptions from retail bank. This serves to direct scarce human and capital resources towards high potential customers defined by the predictive model. The data set with which the model was trained consists of features relating to client information, product detail, and socio-economic indicators, having eliminated the contact center related data. So the Spark ML library from the Apache Spark distributed computing engine was engaged alongside the PySpark API for modeling. The random forest model is preferred for its robust performance, lower computational cost, and amenability to parallel computing. Thank you very much.